Hello, welcome to the pre-recorded version of my talk for IMAC 2022. My name is Matt Allen. I'll be presenting on behalf of my co-authors, a graduate student and an undergraduate student at University of Wisconsin-Madison, and Jacob Capito is an undergraduate at Brigham Young University. My talk is on joints, and as you may or may not know, joints are one of the main sources of damping in structures, built-up structures, and also a really common source of nonlinearity. And they're incredibly complicated if we get into every possible detail. I mean, joints, we even need to think about chemistry down at the atomic scale and the strength of bonds between different materials. So these can be incredibly complicated. What our talk looks at today is if we stop our focus here at about the millimeter scale, or about like the contact mechanics scale, can we predict the damping that a structure will have? So as you know, if we didn't have any joints, we'd be lightly damped. The joints tend to add a lot of damping, and we're wondering, could we predict that using a finite element model with Coulomb friction, focusing on this scale and not worrying about a lot of these features that happen at lower scale. So one of the things that prompted this study is we collected a thorough set of measurements on a structure called the S4 beam, which is two beams bolted together, one bolt at each end. And so there's about a 1.5 by 1.25 inch contact area on either end of the beam. All the contact happens there. And when the beam vibrates, that puts stresses on these joints. We also implemented load cells so that we could measure the preload in the joints very accurately. We found this to be really important, as the torque was not a great metric by which to control preload. And we'll get into some more on the measurements in a bit. By the way, if others are interested in using these same measurements, they're available in our MSSP paper, and there's a website where you can download most everything. So what are we trying to capture here? Well, when a structure vibrates, friction in the joints causes damping. And how does that happen? Well, we start with a nominal structure, we put a bolt in, and then we preload it. And in an exaggerated sense, this is what the deformation would look like around the joint. And because of this, this Poisson effect, this peeling up, and also just the fact that the contact pressure goes out in kind of a cone, it doesn't necessarily spread to the entire surface, you end up getting usually an area of contact and an area where there might be no contact or very little contact. Maybe a better way to think of that is in terms of pressure. You get an area of very high pressure around the center of the bolt, and that pressure decays down to 0 or near 0 at the edges. So when the structure vibrates then, making a deformation like this, there's always a region on the edge of the contact where the pressure is really low. And therefore the joint can slip there. And so in each cycle of vibration, you get slipping and sticking and slipping and sticking. And that dissipates energy. When you put all that together, what that does is, if you were to think of a single mode of vibration, as vibration amplitude increases, you get more and more slipping. So you get a bigger and bigger decrease in the natural frequency of the structure. And you can also get a big increase in the damping of the structure. And typically the frequency shifts are relatively small. You can think of this as, think of how big of a change in the natural frequency would you have if the bolts were, say, in contact but loose, right? So they're still holding the parts together, but the contact surface can slide in this horizontal plane as much as it wants. So that the shift in frequency tends to be small. So from that standpoint, the nonlinearity is weak, but the damping sometimes can change by an order of magnitude or more. And it's not at all uncommon to see factor of 2 increases in damping with amplitude. So from that standpoint, the nonlinearity is very important. And so this is what we want to see if the finite element model could predict. I should also mention that, typical models like we use in system identification, like where we assume the nonlinearity is just a polynomial in displacement and velocity, a model like that cannot capture this behavior very well. It might capture, this behavior over a very small range of amplitude, but it definitely can't capture this power law effect where the damping and the amplitude are linearly related on a log-log scale. One challenge in doing all this, and why this hasn't been done before, is because it's extremely expensive. If you were to just take the model that I just showed you and turn on nonlinear contact in Abaqus, and then run a dynamic analysis to try to replicate the experiment where we hit this with a hammer and we watch the response decay down to 0, by our estimations, you'd need tens to maybe even hundreds of years to complete an analysis like that. And it doesn't speed up all that much if you increase the number of processors. At least in our experience in Abaqus, it doesn't speed up a lot. So clever researchers have come up with a lot of alternatives. There's some great harmonic balance algorithms. One of them mentioned here, the force algorithm, that could come up with kind of the similar kind of information in the frequency domain in a matter of days or maybe weeks. Very recently, there's been an algorithm developed that uses interface reduction, and it's been tried out on this type of model. And again, that seems to be able to bring the time down to days or maybe weeks. We're going to use something called Quasi-Static Modal Analysis, well, I'll explain in a minute, which can allow us to do, to basically derive these characteristics that we're after in only a matter of days. All right, so quasi-static modal analysis, what is it? The idea is that when the structure vibrates, it's going to deform in a certain shape. So we apply a static force that tries to bend the structure into that shape. And in doing that, it's important that we apply a force and not a displacement, because if we applied the displacement in the shape of a mode, the whole contact surface would remain stuck, because at low amplitude, there's no slipping in the joint. Because we apply a force, the joint is allowed to slip, and so it can exhibit its nonlinearity. Once we have the force displacement curve from that static analysis, that would be the orange curve is what we would get solving that static problem. We can use Masing's rules to calculate then what the response would be over one cycle of vibration at that same amplitude. And from that, we can calculate the frequency using a secant to the curve, and we can calculate the energy dissipated as the area enclosed by that curve. And that gives us the natural frequency and the damping ratio of the mode in question. So that's the basic idea. And then using a subset of this force displacement curve, we could also calculate the hysteresis loop over a smaller amplitude. And so we can characterize the whole force, the whole vibration amplitude dependent frequency of damping from one load displacement curve nominally. So here's a picture of the finite element model that we're using, about 1.2 million degrees of freedom. And a very fine resolution was needed. After much trial and error, we discovered that we needed a very fine resolution of elements around the contact so that we could capture the contact pressure accurately near the bolt. And so that was the major constraint on the size of the model. A lot of elements were required in this area. And then everywhere else, we made the elements as large as possible without having too big of aspect ratio issues. So there's one bolt on each end, and the preload force was pretension is applied to the bolts, which gives the preload in the beam. All right, and what I'll show you today is the summation of dozens of analyses. We estimate that we did more than 50, attempted probably much more than 50, a lot of failed analyses, a lot that failed to converge or crashed. And each one took between 2 and 7 days, depending on whether we include all the time required to convert the results so we could load them into MATLAB for analysis and some of those things as well. So what I'll show you today is thousands of CPU hours worth of effort to study this relatively simple structure. But it's one of our first times doing this, so we had a lot to learn. So these are the modes of the structure, just so you can get an idea of how it moves. We're focused on mode 2 because this puts a lot of stress on the joint, as you could imagine, and mode 6. And the experiments also confirmed that these were the 2 modes that exhibited the most nonlinearity. And so they're the ones we wanted to study. Modes 4, 5, and 3 were pretty much insensitive to the joint. So the joints didn't really matter much there. So you could model these modes without worrying about the joints. The first mode, its natural frequency was also sensitive to the joint, so we'll talk about it a little bit. One of the first things we discovered was that our original model, which had a nominally flat surface and a contact pressure that would look like this, when we changed the preload, the natural frequencies didn't change, and that's what you would expect for a flat-on-flat interface based on contact mechanics. But the actual measurements, when we tightened the bolts, the natural frequencies shifted. And so we realized fairly early on that we needed to capture the surface topography, the shape of the contacting surfaces, and that those must not be flat. And so these show pictures of measurements from a coordinate measuring machine where we captured the interface shapes. And sure enough, if you look at these color bars are in thousandths of it, or in inches. So it's less than 1,000th of an inch or a few microns out of flat. And yet that changes the contact pressure significantly. So we looked at a few different ways of quantifying that. One was to actually take those measurements, smooth them in some way. These 2 figures here show smoothing with a locally weighted smoothing method, and then applying the smooth surface measurements to the actual finite element model. So we would take and perturb each node in the finite element model to follow the measured surface profile. So we did that. There are 3 different levels of smoothing that we studied with what we call the lowest method, or MATLAB calls the lowest method. And then we also tried a much simpler approach where we just said, suppose that we approximate the surface as a sphere with a certain radius of curvature. If we can just estimate the radius of curvature, can we get a good enough approximation to the surface geometry? And so this shows a few of the radii of curvature. We studied several to try to understand how well that would approximate the behavior. So you'll see several different models with different R values, different radius for spherical curvature, or different smoothing for Loess. And this gives you an idea of how much that changes things. So again, this was the contact pressure of the flat-on-flat surfaces. And when we applied the measured interfaces with different levels of smoothing, you see that the contact pressure changes significantly. And so you can see that you definitely lose some fidelity as you come up to more and more smoothing. But in terms of capturing the damping, the nonlinearity, the natural frequencies, we don't yet know how much resolution we need. The first thing we looked at were the linearized natural frequencies. So we calculated the natural frequencies at 2,000 pound preload, and then as we decreased the preload, we looked at how much each of those natural frequencies shifted. And the blue in each of these plots is the experimental shift in the natural frequencies. So mode 1, mode 2, and mode 6. And these are the spherical curvature models, and these are the Loess models. And what we found is that, well, all the models actually get in the ballpark pretty well. Here, it seemed that the R equals 2,000 or R equals 4,000, so 2 to 4,000 inch radius of curvature seemed to do a good job, pretty good job of capturing the frequency shift in a lot of these modes. There are definitely some places where that doesn't hold, but for the most part, that seemed to do a pretty good job. Mode 6 had the biggest shift in the natural frequency, which was the torsion mode. And so that's one of the biggest changes there. And the biggest shift at the lowest preload was pretty well captured by these models. Similarly, the lowest models captured this well. Maybe the lowest 10 sometimes was over-predicted a little bit. The others seemed to be slightly better. But this was encouraging, where we thought we could get a pretty good idea of this effect with either of these models, and a pretty good agreement with measurements. So that was encouraging. So then we started to look at nonlinearity in the joint. And again, when we bend the structure into the mode of question, what happens in the interface is that we get slipping. And so this is for the spherical interface, a 2,000 inch radius of curvature. And so as we increase the displacement in the shape of this mode 2, you eventually start to see slipping. And it's important to look at this when we do this modeling, because it's not until you get significant regions of slip, significant amounts of slip, that you see any softening in this quasi-static response. And so if you were to analyze, say, data just from this top row, you'd see basically no nonlinearity, and anything you see would be dominated by error in the solver. And so we ended up discovering that this was a really important metric to look at. Also, it tells you how important the mesh density is. If your mesh is too coarse, you don't have enough elements to slip, and you won't resolve this effect. I mean, you will eventually resolve it if you get to large enough forces, but if you want to capture a certain force level, you need a mesh that matches. So this was one of the lessons learned. Eventually, though, we did, after many trials and a lot of trial and error, we did learn how to model the structure. And then we were able to start to do some analyses. So one thing we looked at is the effect of the surface smoothing, and surprisingly, there's a very big difference in the surface topography between the lowest 10 and the lowest 50, or this one is smoothed a lot more than the one on the top. And yet, when we calculated damping ratio versus amplitude for mode 2, you see that there's a big difference between those surfaces and the flat interface. But between each other, there wasn't a significant difference in the amount of damping. And so this taught us that while the surface topography is important, every little detail of the surface topography doesn't seem to be as important. The damping is the net effect of slip along the entire interface, and so maybe that tends to smooth things out quite a bit. So that's encouraging in terms of making this practical for future use. So with all of that, we're finally ready to start comparing our predictions with measurements. So the black dots here are measurements of the damping and the shift in the natural frequency of mode 2 versus vibration amplitude. And this is for the lowest preload, 500-pound preload. And at first we were a little discouraged because the flat model was the one that was predicting the damping the best. All of these other models which more accurately capture the natural frequencies. Remember, the flat model wasn't able to predict the natural frequencies at all. But these models were under-predicting the damping by almost an order of magnitude. And they were predicting the onset of the stiffness nonlinearity to be, maybe not quite an order of magnitude, but quite a bit later than it actually happened. So this had us wondering what was going on. All of these models used a friction coefficient of 0.6. So we also varied the friction coefficient 0.1 and down to 0.1 and 0.2. And we found that with that, a friction coefficient of 0.2 would get quite relatively close to capturing the damping and the natural frequency. If we decrease the friction coefficient even more, we get more damping, and we get, in some ways, a better agreement, though then the model predicts that the structure starts to go into macro slip at these amplitudes. And we have measurements in that range that tell us that the real structure actually didn't go into macro slip. So we think that that is pushing things a little too far. But the model with mu somewhere around 0.2 does seem to capture these measurements pretty well. So this is only one mode, though. Does the same thing hold for a different mode? So next we look at mode 6, the torsion mode at 500-pound preload. And this time we'll look directly at the different friction coefficients, 0.6, 0.2, 0.1. And the conclusion is fairly similar. Mu of 0.2 does seem to do a pretty good job of capturing the measurements. If we go higher than that, we do seem to go into macro slip too early. And I guess we should mention that in these measurements, we actually did get a few data points down at a, not sure if it's total macro slip, but where there's very significant slip in the joint. So in the frequency shift here, these couple data points were a solid measurement of where the structure would go when it slipped quite significantly. And again, with mu somewhere around 0.2, we do seem to capture that. There's a very noisy region in here where there seemed to be maybe some modal interaction or something. And we don't have time to go into that in this talk, but you could look at that in the data if you were interested. And then the power law behavior down here was the of interest. So again, the model does seem to be able to predict that reasonably well, and we thought that was encouraging. We also looked at increasing the preload, and we repeated everything. When the preload increases, the damping goes down by about an order of magnitude. And so the damping ratio here is quite a bit lower than what I showed earlier. And again, the mu equals 0.2 model does seem to capture that reasonably well. And we could do the same for mode 2. We saw similar conclusions. So in conclusion, our study does show that a model with millimeter scale friction, using Coulomb friction as our friction law, does seem to be able to predict the behavior of our structure in a pretty thorough way. It can capture the preload effect on the linearized natural frequencies, and it also seems to capture the nonlinear frequency and damping that we observe in measurements. And while it was important to capture micron scale topology or deviations from flatness in the surface, it didn't seem really important to capture every little detail for these surfaces at least. And so it seems sufficient just to approximate the surfaces as spherical and to have a reasonable estimate of the radius of curvature to be able to predict the nonlinear dynamics. So with that, we were able to predict the damping and the nonlinearity, the power law nonlinearity and the damping as a function of amplitude. And so this could be a big step forward in a lot of industries, we hope. In closing, just want to acknowledge some of the funding agencies and thank the students, especially my 3 co-authors who helped on this work, and also many of the students who laid the foundation for this work through their master's and PhD theses. And with that, I look forward to taking any questions from you at the conference and hope to see you there in person or online.